This is the complex numbers lecture that you've always been waiting for. And this is for Wednesday, October 16th. We'll review this in class then. Okay, so I'll move forward. The imaginary number I. We need to talk about the imaginary number I, which is the square root of -1. Square root of -1 comes up often when we do calculations, and so mathematicians at some point said, let's make this represented by a special character I. So whenever you see I, the imaginary number, that's what it represents, is the square root of -1. So for instance, if I wanted to take the square root of a negative number, and I have -25 here, using standard sort of procedures, we can divide this up into the square root of -1 times the square root of 25. Square root of 25 is plus or minus 5. The square root of -1 is I, and so we get a square root of a negative number. Remember that square roots can be plus or minus. The standard sort of convention is just to acknowledge the positive one, but I want to remind you as we move forward, we might have to remember the negative one as well. And as we're moving towards quadratics, what this lets us do is solve an impossible quadratic formula. In a situation where we would have ended up with a negative sign below the square root, we now have a technique to be able to solve that. For example, I have this equation here, which is a downward facing parabola, which is displaced below the x-axis, and so it'll never cross 0. If I tried to solve this, a equals -3, b equals 4, and c equals -2. Let's plug this into the quadratic formula here. So -4 plus or minus the square root of 4 squared, which is 16, minus 4 times a, -3, times c, -2. We're already seeing that there's going to be a negative sign in the second term here. I'm going to go ahead and put this over 2a, which is over 2 times -3. Let's evaluate what's under the radical. So we get the square root of 16 minus 12 times 2 is 24. Ruh-roh. You're already seeing this over -6. So we get -4 plus or minus the square root of -8 over -6. If I simplify this a little bit further, I can divide by 2, or let me evaluate the square root. I can get 2 the square root of -2 over -6, -8. I can divide by a factor of 2, so I get -2 plus or minus the square root of -2 over -3. I can divide this up. If I look at the first term, I get 2/3 plus or minus. Well, now I know that the square root of -2 is going to be I times root 2 and divide by 3. So when I look at the solution, I'm going to have an imaginary number here, which makes sense. Like I said before, we're going to have a downward pointing parabola, and we're trying to solve when it crosses the x-axis, and it doesn't. And that's what this equation is saying, is that if you get an imaginary number, it won't cross the x-axis. So that's how we can represent negative roots and get imaginary numbers. So what we're going to look at, and what you just noticed, is that I had a complex number. The definition of a complex number is the sum of a real number and an imaginary number. And I have an example here, -2 plus 3i. There's a real portion here, which is just the first part, the real -2. Anything that has the I associated with it is going to the imaginary part of that complex number. What happens is we can express this as an ordered pair. A lot of times we will express this as an ordered pair. There's the real portion, and then there's the next part of this ordered pair is just the coefficient in front of I, the imaginary coefficient. So it looks like a point, and you may recognize this as a point. We could plot it on a Cartesian coordinate system. And so that's how mathematicians have conceptualize the real and imaginary plane is instead of having an x and y axis, we're going to have a real axis and imaginary axis. And you can see I plotted, or your book has plotted this negative 2 plus 3i as a point here, negative 2, 3, because it's negative 2 on the real axis and 3 up on the imaginary axis, and then we get that point. So that's convenient. You can do interesting things with that. We're not going to go much into that, but you may see that more in different math classes. So we may want to add or subtract complex numbers. What happens is our strategy is to add or subtract the real parts and then separately add or subtract the imaginary parts. All right, and I have an example here from the previous page, negative 2 plus 3i. Well, I'm just going to add I'm going to add it to itself is what I'm going to do. So I'm going to take the two real parts, right? So here's a real part and here's a real part. Negative 2 plus negative 2 is negative 4. And then the imaginary parts, I'm going to have 3i plus 3i, which is a plus 6i. And that's as simple as adding. When I subtract it from itself, I'm going to need to distribute the negative sign. So I get negative 2 plus 3i plus 2 minus 3i. Ooh, is this what I expect it to be? I get 0 plus 0, which is 0. Okay, and you see that? I have the real parts here, negative 2 and plus 2. I have the imaginary parts, plus 3i, negative 3i, and I get 0. So adding and subtracting complex numbers is as straightforward as that. You just isolate the real parts, isolate the imaginary parts, and treat them separately. We're going to move forward to multiplying them, and what I need to talk about here is factors or multiples of I, exponents of I. And so what I'm going to remind you is that we define I to be the square root of negative 1. We're going to keep that in mind as we move forward and evaluate the rest of these terms. I squared. If I think about I squared, I'm going to write down what I know. I squared is the square root of 1, right? It's I times I. So I times I is the square root of negative 1 times the square root of negative 1. Let's be clever about this, though. The square root of negative 1 twice multiplied by each other is the square root of negative 1 squared, which is negative 1. So we can write out I squared equals negative 1. Very convenient. We're going to keep this as we move forward. If I want to evaluate I cubed, well, I'm going to recognize I cubed as I squared times I. I'm going to recognize I squared as negative 1, as I figured out in the line right above, negative 1. And I still have the I term, so I get negative I cubed equals negative I. This is an interesting pattern, right? I to the 4th power, we're going to have the same trick as the line before. I'm going to divide it up into I squared and then multiply by I squared again, right? 4 is 2 factors of 2. So I'm going to remember from my second line here, I squared is negative 1. And I have 2 factors of negative 1, so I to the 4th is 1. So these are the base sort of exponents of I. If I moved on to any algebra which results, we can use the above factors accordingly. So if I want to use I to the 5th power, I'm going to recognize that as I to the 4th times I. I to the 4th is 1, and I is I. So I to the 5th power is just I back again to the 1st power. Interesting. So all of the factors, exponents of I, can be reduced down to I squared, I cubed, I to the 4th. All of them can be reduced down to a factor of I multiplied by a positive or negative constant. Let's do I to the 6th. I to the 6th I'm going to recognize as I to the 4th times I squared. I to the 4th is 1. I squared is negative 1. So I to the 6th power is negative 1. And so when you see exponents, what you'll do is you'll divide them up into these base exponents. I to the 4th, I to the 3rd, I squared, I to the 1st, and move from there. So I put a more complex one down here. If I looked at I to the 31st, I could write it out like this. I'm going to divide 31 by 4 and I get 7, right? So I can have I to the 4th 7 times. Remember, that's I to the 28th power. I'm going to have, after that, so 28, I still need to go up 3, so I'm going to have I squared and I to the 1st power. Notice overall, when I add the exponents, I'm keeping to the 31st power. 28 plus 2 plus 1 is I to the 31st power. But I'm going to simplify what I've written here. I to the 4th I recognize as 1, so I get 1 to the 7th power. Ooh, that's easy to evaluate. I squared is negative 1, and I to the 1st is I. So I to the 7th power is just 1 times negative 1 times I. I to the 31st simplifies down to negative I. Very interesting. So keep this trick in mind as you move forward. Divide by factors of 4, divide by factors of 2, divide by factors of 1, and reduce down to a simple expression with I to the 1st power with positive or negative constants out front. And we'll do more examples like of this in class. I'm going to move forward to the next slide here. So we're going to multiply complex numbers, which is pretty interesting. I'm going to remind you also about foiling. Because we have 2 terms in each factor that we're multiplying together, we're going to have to remember to FOIL these. The example that I put here is pretty straightforward. Let's go ahead and FOIL this. Negative 8. All right, negative 2 times 4 is negative 8. First, outers, negative 2 times negative 5i is going to be a plus 10i. Inners, negative 3i times 4 is a positive 12i. And lasts are positive 3i times negative 5i is a negative 15i squared. Notice I'm going to get an I squared here. So let's simplify this term. I'm going to keep the negative 8 there. I'm going to combine my I terms so I get plus 22i. And then let's evaluate this down here. Let's remember that I squared. Remember what I squared is? I squared is negative 1. So I get negative 15 times negative 1, which is a positive 15. So notice that I can combine my negative 8 and then the positive 15. So overall, I'm going to get this 7 plus 22i. Okay, notice that I will reduce all of the terms down to either a real portion of just a number or an imaginary portion of I to the 1st power. I can't leave I squared in there. I squared or I cubed, I to the 4th, they're always reduced down to negative 1, negative I, or I. Okay, so let's practice on the next one. I have 2 terms multiplied by each other. Let's go ahead and FOIL this out. I'll go ahead and do this quickly here. Plus 6i plus 6i plus 9i squared. We're going to simplify again. 4 plus 12i. I'm going to note that I squared is negative 1, so I get minus 9. So this simplifies down to negative 5 plus 12i. Interesting. All right, we're going to practice more in class here. This last one I chose, and notice what's going on here is it's the same term with 2 different signs in the middle. You may recognize this as a difference of squares sort of situation. If I FOIL this out, 4 minus 6i plus 6i, ooh, I like the looks of that, minus 9i squared. Notice that the 2 terms in the middle, because there's a plus and minus sign, they're going to cancel each other out. Minus 6i plus 6i, those kind of disappear. So I'm going to have 4 minus 9i squared. Let's remember that I squared is negative 1, so I get plus 9. And this whole term turns out to be a single real number with no imaginary component. And that's what will happen when you have the 2 different signs in the middle. We're going to keep this in mind as we move forward as a technique to reduce factors of I, okay? And that's why I put this here. Like I said, we're going to practice more multiplying in class, but I'm going to move forward to the next slide that talks about dividing complex numbers. And related to this is an important concept of complex conjugates. Okay, so mathematicians have this rule. We can call one of them up and ask them why. I'm not sure why. The convention here is you cannot express with an imaginary number in the denominator. And you may recognize this as the situation where you cannot divide by a radical. It's very similar in terms of notation and expression for rules for mathematicians. I'm not exactly sure. For instance, you may get an answer of 1 over root 2. In order to reduce the radical out of the denominator, what we do is we multiply by the same radical on the top and bottom. This is a factor of 1. We're not changing the term because we're multiplying by a factor of 1, but what it allows us to do is to reduce the radical out of the denominator, and notice that it's up top. So we must reduce until no imaginary numbers are left in the denominator. Let's keep that in mind as we move forward. This is a rule and convention. So how do we do this? When a complex number is in the denominator, we have to multiply the top and bottom by the complex conjugate. So this term here, complex conjugate, is a very important concept. And what that means is we negate the imaginary part of a complex number. Whatever portion of it is the imaginary part, whatever sign is there, we just negate it. So for instance, I have 1 over 2i. The negation of 2i is negative 2i, so I'm going to multiply by a factor of 1, which is negative 2i over negative 2i. Let's multiply this out. And you can see I did that there. I get negative 4i squared, and then I get negative 2i on the top. I'm going to remember that I squared is negative 1, so I have negative 4 times negative 1 into the denominator. I left the negative 2i up top. And notice that this simplifies down to negative I over 2. I do not have an imaginary number in the denominator. It's only in the numerator. And this is what mathematicians like. This is the convention. So let's do a couple of examples so that we can see a little bit more how this works. All right. So I did this one on the previous page. Let's look at this. In order to reduce negative 5 over 3i, I'm actually going to let this be negative 5 over 3i. I'm going to multiply by the complex conjugate. So if there's a positive 3i in the denominator, I'm going to multiply by negative 3i on both top and bottom. So the bottom becomes 3 times negative 3 is negative 9. I times I is I squared. On the top, I have negative 5 times negative 3i, which is a positive 15i. I squared is negative 1, so I get 15i. Negative 9 times negative 1, which is 15i over 9. Let's reduce this one more step. I can divide the top and bottom by 3. Yes. So we get 5i over 3, and that's the final answer. Notice that the initial term was negative and this one's positive. Very interesting. That's all right. That's just how that works sometimes. I picked a more complicated one here because I wanted to show you when there's a real and imaginary portion. Okay. So in order to get the imaginary number out of the denominator, I'm going to multiply by the complex conjugate, which means take the negative, negate the imaginary part. So I'm going to leave 1 by itself. Leave it there. It stays the same sign. The only thing that changes sign is the imaginary part. So I get negative 2i. And then because I want to multiply by a factor of 1, I'm going to multiply the top and bottom by the same thing. So I get 2 minus 4i times 1 minus 2i over 1 plus 2i, 1 minus 2i. Let's FOIL the top, and then notice on the bottom I have this opposite sign going on. And you may remember from the previous slide, when I have these opposite signs going on in the middle, I'm going to end up with a real number only in the denominator. Alright, let's multiply, FOIL out the top. 2 minus 4i minus 4i plus 8i squared over 1 minus 2i plus 2i minus 4i squared. I'm going to simplify one more step here. So 2 minus 8i, I'm going to remember that I squared is negative 1, so minus 8. And on the bottom, I get 1 minus 4i squared. I'm going to keep simplifying. Negative 6 minus 8i over 1 plus 4. Remember, I squared is negative 1. Negative 1 times negative 4 is a positive 4. So I'm getting negative 6 minus 8i all over 5. That would be the simplest version. An alternate version would be to do this. The negative of the quantity 6 plus 8i over 5. Notice that there's no I in the denominator. We simplified all of this down in order to have the I only in the numerator and a real number in the denominator.